let's talk about continuously compounded interest very briefly. The usual compound interest formula, this is where we're going to start. A of t, the amount of money in our account after t years, the initial money, the principal, times 1 plus the interest rate over the compounding frequency, that's how many times it's compounded per year, all to the nt. So what that does is nt is how many times you get paid, how many pay periods there are, and how many compounding periods, and the 1 plus r over n factor is by how much your account grows every time it's compounded. So let's assume we're good with that. And then there's some various observations we can make out of this, but I'm just going to focus on one observation, very much like the book does. And that is that if we strip this down to the most basic case, let's say I put in $1 at 100% interest, so R is 1, 100% is just 1, and I just leave it in there for 1 year. That's a very good test case for how this depends on n. And what we discover is that when n is very large, this stabilizes at this magic number e, which is 2.71828, 1828, something like that. Okay. And we don't ever need that many decimal places, but about 2.72-ish. And so this is a very interesting thing. What it really says is that when we compound very often, if n is very large, it doesn't matter exactly how large it is. The compounding frequency doesn't matter very much, as long as it's large. And the other thing it says is that it allows us to use a simpler approximation. If n doesn't matter, why is it in our formula? Let's try to find a formula where that's not in there. Okay. And indeed, this is the simplest case. When you've got n being a large number, we can approximate it just by this single number e, this constant e that doesn't depend on n. Okay, but what about if we put everything else back in? If we put in all the complication back in, then there's a couple of ways we could simplify that. First of all, the p is just multiplied on the outside. So if n is large, if I can figure out what this is doing in terms of this magic number e, then I'm just going to multiply by p on the end. Then there's another thing I can do, which is using rules of exponents. I can take this to the n and then to the t. Basically what I'm doing sort of in terms of the finance is I'm focusing on this part is the growth factor after t years, and I know that if I just multiply that by what I started in the account, then I'm going to be good. And then what I actually do is this is the growth factor for 1 year. If I know it grows, say, by 1.7 in 1 year, and I'm in there for 10 years, I'm just going to take 1.7 and raise it to the 10th power, because I'm just multiplying by 1.7 10 times. And then I multiply by p. So it's really figuring out this that's the key thing. And this is really close to what we know from here. If n is large, this number is just e. Ooh, but there's this r in here. And that's where we have to be a little bit more sophisticated. Okay, so we need a little change of variables. And this is where algebra really gets good and interesting. We've used a little bit of algebra, like the rule of exponents here, but that kind of took something on the outside of the expression and separated it out. We now need to take something deep on the inside of this expression and somehow deal with it. And so what we're going to do is we're going to do a substitution. I'll use the same letter that the book does. We're going to let m equals n over r. And that's going to allow us to express this in a simpler way. And it's going to turn this into something that looks like this. The wonderful thing about algebra is that using substitution, you can just kind of, to some extent, you can sort of make things look the way you want them. Okay, so I've got 1 plus now 1 over m, because r over n is just the reciprocal of m. Okay, to the, well, you know what? I'd really love it if this were just the letter m, but it's not. Okay, but what do we know? If m equals n over r, then n, oops, math mode, n is going to be rm. Rm. And then it's all to the t. Okay, now I can use the trick I used before, that I would like to get 1 plus 1 over m to the m here. That r is annoying, but that I can export out using rules of exponents. So it's a combination of the substitution, which is the really subtle thing here, and rules of exponents. And so now I'm going to have that to the r and to the t. So in fact, the RT actually comes out here. Okay. So focusing on this quantity, n over r, not how many pay periods there were, but how many pay periods there were related to the interest rate. That turns out to be the crucial thing. Okay. So now we're going to do is we're going to assume m is very large. Oops. So this quantity here is very, very close to the magic number e. Okay? And so this whole thing, one more time, is going to be very, very close to p times, all this goes away, magically, boom, it's just e to the rt. And you get pert. Okay? So in fact, you can think of it two ways. You can think of it as just an approximation that really probably we're really just compounding like a lot. And this is an approximate answer. So you can think of as an approximation, or you can think of it as an idealization. It's just kind of a subtle shift of perspective. In other words, let's actually just say there's this sort of ideal perfect world where we get a tiny little continuous trickle of money into our account every instant, sort of every infinitesimal little bit of time. Then this would be the exact formula. And the difference is not that big. As long as this m is really large, either r is small or n is big, then this is going to be a really good approximation. It doesn't really matter. But you often see it as an equality for this idealized case as opposed to an approximation. So there's PERT. Okay, so for example, if I let's see, if P, let's say I start out with $1,000 and the interest rate is 5%, which is really, 0.05, got to be careful to plug it in right. And the time, let's say I leave it in there for 40 years, say kind of a retirement scenario. And the n is pretty big. Let's say it's compounded daily, 365. Okay. Then let's look at what this crucial number n over r is. It was really that needed to be big. So let's just check to make sure that seems like a pretty big number. M is n over r is 365 over 0.05. And so that's equal to 7,300. That's a pretty big number. Okay. So we can confidently use the approximation. And so we just go ahead and say PERT instead of all the complicated version. And so we get $1,000 times e to the 0.05 times 40. And we don't put in the 365 at all. We just made sure that 365 was a pretty big number. Okay, or really it's the 7,300 that was big. And I just evaluate that. Let me evaluate it numerically because I don't know if it'll, yeah. Okay, so about $7,389.10 we get at the end of that. That's pretty good. That's a lot more money than we started with, but we did put it in for 40 years. Okay.